sisters to this world. In a town where blood ties are only blood. If you never say your name out loud to anyone, they can never ever call you by it. If I kiss you where it's sharp, if I kiss you where it's sore, will you feel better, better, better? Will you feel anything at all? Will you feel better, better, better? Will you feel anything at all? You get sad, get sad, sad. Don't understand, don't understand. But if I kiss you where it's sore, if I kiss you where it's sore, will you feel better, better, better? Will you feel anything at all? Will you feel better, better, better? Will you feel anything at all? Will you feel anything
Welcome back. This is week 4 of Computer Science 3, CSCE 310 here at the University of Nebraska-Lincoln. And we were going to continue where we left off on Friday with Prim's algorithm, minimum spanning tree algorithms. And then we'll also try to cover as much as we can today of shortest distance algorithms, both Dijkstra's algorithm and Floyd-Warshall's algorithm. So let's go ahead and get started. And as a quick review here, remember that Prim's algorithm, in contrast to Kruskal's algorithm that we already looked at, does not do cycle detection because it only builds a tree outward, and it only looks at these things called tree edges, tree vertices, fringe vertices, and un unvisited or unseen vertices. And I've got that illustrated right here in this diagram. The green on the left here, these are the tree edges. So we've jumped into the middle of the algorithm here that we already went through on Friday. And these green vertices, that's the tree that we've built so far. So we're not going to look at things, for example, C to E over here. That has a that would be the minimum weighted edge that we would take next if it was Kruskal's. But we're not going to look that far away. Instead, we're only going to look at local information here along the fringe of this. We're only going to be looking at vertices that connect B, E, or G to our current tree over here, which of course would be this vertex right here, or this edge right here, connecting A to B, D to B, D to E, and F to E. So a couple of things to note here. First of all, this is highlighted in red right here because that's the one that we would end up taking on that iteration. But another thing to note here is that when we've got multiple edges connecting to the same vertex over here, we're probably going to keep track of those. In other words, D to E and F to E, well, we know that if we ever connect those, we're never going to take the one that's weighted 15 because we're trying to minimize it. We're only going to ever take the one that is weighted 8. But we are still going to maintain that in a data structure, and I'll show you why here in a second when we actually come up with the pseudocode to do this. Okay, so let's go ahead and do that now. Let's make sure I've got. Go ahead and go with blue. All right. So here's Prim's algorithm. All right. Our input is going to be just as before. A weighted graph G equals V comma E. And the implication here is that it is undirected, but that doesn't that's not a big deal. So we're going to output the minimum spanning tree of G. Right? Let me try to write a little bit bigger with a different color over here. Let's try this. So what kind of data structure would be useful here? Let's think about that for a really quick second. And remember that we are on live Q&A with Piazza. So if you've got questions or want to draw my attention to some issue, please please do so. For example, so how do we maintain these edges over here? We've got 1, 2, 3, 4, 5 edges at this point in the algorithm that we want to keep track of. But what we want is the next least weighted one. So a perfectly suited thing where we can just put stuff in, but when we take it out, we take the minimum value is probably going to be a min heap, right? So I'm going to go ahead and create a min heap here. I'll call it H. In the pseudocode in the lecture notes, I think I call it Q, and that's because a min heap and a priority queue are the same thing. So we can have a priority queue here instead. This will be a min heap, and which stores edges, and it'll store the edges according to their weight. And since it's min heap, every time we dequeue something or every time we get the minimum out of this heap, we're going to end up getting the minimum weighted edge. Okay, so we need to start the algorithm, and we'll start the algorithm with an edge set that corresponds to the trees. We've already got our vertex set and our edge set over here as the input, but we need to make this output here, this minimum spanning tree of T. So we need to initialize both an edge set and a vertex set. So initially, we're going to start. Now remember this picture up above here, that's the algorithm that we've jumped into after 2 or 3 iterations. Initially, we're not going to have any edges whatsoever, right? That's going to be the empty set. Now, the vertex set, we're going to start that with an arbitrary vertex. I'll just start it at the first vertex. Or again, this can be an arbitrary vertex. It doesn't matter where you start, you're going to come up with an equivalent tree. You could, if you start at one vertex versus another vertex, you could come up with 2 different minimum spanning trees, but they're going to have the same total weight. So you could come up with different spanning trees, but they're both going to be minimal. Okay. Now what I'm going to do is, before I go into a loop here, I'm going to enqueue the neighborhood of that initial vertex, all of its edges, neighborhood's edges into H. All right. So again, we're storing edges. You can think of it as storing the vertices if you really want to, and then associate that with a tuple or a pair. Here's the vertex. Here's the edge that it corresponds to, so that there'll be multiple vertices in there potentially at any one point, but the edges are only get in there once. Okay. So while Q, or I've renamed it H here, is not empty, right? Or another way that you can do this is you can do it the same stopping condition as with Kruskal's, that once you've built the tree, in fact, I think you could probably get away with just iterating over this n times, yeah, or alternatively, iterate n minus 1 times. Why n minus 1 times? Because each iteration we're going to add a vertice or vertex, and we start out with a vertex, so we only really need to go n minus 1 times. All right. Get myself some more paper prepped over here. So what we're going to do is we're going to pull out an edge with endpoints x and y, and this will be h dot dq, right? And again, I'll comment here. This is the minimum weighted edge on the fringe, or the frontier is what I think I was calling it on Friday. Okay, so on so weighted fringe edge. Okay, you're letting the smart data structure do your work for you, so that you don't have to find that edge. Again, if you really want, if you don't use that data structure, then you're going to have to go through and find the minimum anyway, and then that means maybe a linear search, unless you are maintaining an order of some sort or something like that. A heap data structure, usually they're built in. If you're using Python 3, then of course you can heapify a regular old list. Right? So what I want to do is, if x is not in my vertex set so far, or y is not in my vertex set so far, then that means that one of these endpoints is connecting to a new vertex. So for example, over here in this diagram right here, we would say, okay, well, we pulled out A and B. A is in the tree set over here, T sub, or V sub T, but B is not. So what we need to do is we need to take this edge right here. Later on, once we include B, it could come up that D to B is would come out of the queue, but we've already included both endpoints, B and D, in the tree, so we can ignore it, right? So else down here, I'll put it in here explicitly later, we'll ignore it. So at least one of these endpoints is not in my tree yet. So what I need to do is I need to add it, right? Add x or y, that is the endpoint that is not in V sub t, to V sub t, right? The end that is not. And of course, it depends on if this is truly a set here, go ahead and just add both if you really want to, depending on your implementation, because if you add x twice, there's no harm in it. It's a set, it'll maintain, it'll say just no op that it's already in there. And I'll add e to e sub t, because I've taken that edge. In the diagram above here, I've taken the edge from A to B, highlighted in red there. Okay. Then what I need to do is I need to expand my frontier. Once I've taken this edge right here, then that means that B is now part of my tree. And so I look at its neighborhood. I look at A to B, I look at B to D, I look at B to C, and B to E, right? Two of those things are already in my tree, so I don't necessarily have to add them, or might already be in there. But another one of those things is in my my frontier here. I can already get there from D and F, but guess what? I can get there from B at a smaller weight, so I also include that edge, right? I need to include this edge, and I definitely need to include the edge from B to C up here, because that means now I'm taking it out of an unseen area of the graph, and I'm bringing it into my frontier. Now I can actually see it, right? And so I need to add that entire neighborhood to my queue, right? So what I will do is I will enqueue all edges, right? In n sub x, that's the neighborhood of x, or n sub y. And I put an or here, but you can go ahead and write, when you write your actual code, what you could do is you could be more specific. That either x is going to be, here's my tree so far, right? X is going to be in it, or and y is going to be out of it, or it's going to be the case that y is in it and x is out of it. Well, if x is in the tree already, then you don't need to add its neighborhood because it was already added at some point. So whichever one you could say, if x is not in the tree so far, then do everything with respect to x. If y is not in the tree so far, then do everything with respect to y. But you don't need to do it, but to both. Right? That's what I was saying up here. And queue all of the edges in this neighborhood or this neighborhood, depending on which endpoint is not in your tree, into H, as long as the other endpoint is not in V sub t, right? So what I mean by that is, okay, here's the situation with x and y. I'll just go ahead and get rid of this other possibility over here. Suppose that x is already in our tree and we've decided to add this one. Or in this particular more concrete example, a to b, we've already, a is already in the tree. We've just added b to the tree, okay? And then we're looking at b's neighborhood over here. In fact, I'll just do it up here. Now we're looking at b's neighborhood here. Do I need to add d to it? Do I need to add a to it? No, because those are already in the tree. So as long as the other endpoint is not in the tree, then I can go ahead and add it. And that includes E and C over here. It includes E because you still have to include this edge right here because that's a better way of getting to over to E than from D or from F. So you still have to consider those things. Okay. That's the end of the if statement. That's the end of the while loop. There we go. There. Can't display it all, but it's all in the notes. And then we'll output the combination of v sub t and the edge set of the tree, right? There. So again, that while loop condition, while h is not empty, you may have a situation where you are creating a minimum spanning forest instead, and so you would eventually have to exhaust all of the edges and maybe even start over if you want to get the entire forest. This arbitrary vertex that you start at, that is only going to produce a tree that spans its connected component. So if you want to get it all, then you may also need to start over with a different connected component. But that's everything, right? That's so we've got some initialization up here as far as analysis goes. We've got some initialization up here, but the real thing here is the while loop here, right? We're gonna we're gonna dequeue stuff one thing on each iteration of this. And of course, we're going to add things back in as long as we're not duplicating efforts down here. And again, you can go ahead and duplicate the efforts if you really want to, and just go ahead and throw everything back in the queue because the queue is going to be ultra efficient, right? That it's going to end up being like order log m. In order to dequeue something, adding something back in is order log m. You would only ever add an edge maybe and duplicate work twice because you would only ever see that edge twice. After the second time the first time you see it, there's one in the tree in the tree already, and the other endpoint is out of the tree. And so when you finally add that edge and you look back at it, now both of those things are in the tree already. So you don't have, even if you added that second time, you'll never see that edge again because you never consider that vertex again, right? So this is going to end up being order log m. You may eventually have to exhaust all the edges. So ultimately, it's going to be this while loop here is probably going to end up being executed at worst m times, and each time you're doing heap operations, so you're going to go log m, right? And so again, depending on how you represent the graph and what you declare as your input size, this is basically kind of like Kruskal's where you had to pre-sort all the edges anyway, and so it's going to end up being the same thing. But the advantage to this is that you don't have to run a cycle detection subroutine. If that's not your thing, that you don't want to do that. All right, it's not that big of a deal. It's just DFS. But if you want to avoid doing that over and over again, then this does it because you are never adding something back in. If you never consider two vertices that are already in the tree and then adding another vertex that connects them to induce a cycle, because you are only working out from one source here. And then you're iteratively building a tree, and you never add something back in that would, for example, you would never, once we've added A to B, we would then never add B to D, because now both of those things would be in the tree. Okay? All right. So another use of a good, smart data structure, a heap in this case. Okay. All right. Let's look at some shortest distance algorithms. And the first one we're going to look at is Dijkstra's. I need to get the correct spelling. Yeah, Dijkstra's. Right? Shortest. There we go. Distance algorithms. So the reason I cover this one right after Prim's is because it's the same basic idea. What we're going to do is we're going to start at a single, a source vertex. Right? Because what we're going to do with this algorithm is we're going to ultimately produces a shortest path from the vertex I'll give this a name, S, from S to all other vertices. And as we're going to see here, it could be that some vertices are not reachable. That if I start at S, I can never get over to X over there or something like that. Dijkstra's will actually still detect that and tell you that that's not possible. So you can still detect whether or not something you can go from S to T using Dijkstra's algorithm. This works. It works on directed or undirected graphs. And the way that I'm going to show this to you is that we're going to, because it's not entirely, it's more interesting when we look at it with respect to a directed graph, but it works on either one. It doesn't matter with edge weights. Right? So it's dynamic in that it's going to maybe find, I can go from A to B to C with a total weight of, say, 10. But later on in the algorithm, it says, oh, I can actually go from A to B to D and then over to C at a smaller weight of, say, 8. And so it'll actually dynamically update that routing. Right? And it'll also keep track of that routing through what are called predecessor vertices. Right? So I'm going to go ahead and run through an example, and then we'll go ahead and develop the pseudocode here. I'll go ahead and close this now. Here's a completely different graph. All right. And what we're going to do is we're going to start at, say, E here, just because I've got the known answers over here on my left. But of course, you could run this from any vertex. For example, say if you ran it from A, right? A is async. Can you get from A to anything else? No. So you'd run through the algorithm pretty quick without any changes. Everything would be a distance infinite away. And in fact, that's how we initialize everything. From A, I can get to, or from E, excuse me, that's my initial vertex here. I can get to A at a distance of infinity, right? And how do I get there? I need what's called a predecessor vertex. And for now, I'll just go ahead and say that it's nil or null or something like that, because I can't get there. I don't know how to get there yet. I can eventually get there, of course, if you just look at this, you go from E to B over to A. The algorithm will eventually find that route. But initially, I need to initialize everything and say that, how do I get here? Right? Likewise, how do I get from E to B? Well, I can't. It's a distance, and up here, these are vertices, the distance that you can get there from E, and then the predecessor telling you how to get there. And we'll see how these are updated throughout the life of the algorithm here. The one exception here is E. Right? How do I get to E from E? And how much does it cost me? 0, right? Because I'm already there. And what's my predecessor vertex? Let's see, I think it should also be nil or null or nothing, right? or none if you are in Python. Right, there we go. All right, there's my initialization. I am just at E. What I'm going to do is I'm going to branch out here and find more vertices that are reachable at a particular distance. Okay, so the way that I do that is very similar to what we just did with prims. I look at the entire neighborhood. Now, in this case, since it is directed, the neighborhood is a little bit different. H is not in the neighborhood of E because the orientation of that edge goes into E. So the neighborhood, the outgoing neighborhood of E is only B, D, and G. So I'm going to have to update those figures now. All right, well, what about B? I can now get to B at a distance of 5. How do I get there? What's my predecessor? How did I proceed to get there? If I jump into B, how did I get there? Well, E, right? That's the only thing so far. I can go from E to D at a distance of 5 with, again, a predecessor vertex here of E. Right? And I can go from E to G, right? And there's probably going to be a better route there, maybe. Or maybe not. I don't know. We'll find out. At a distance of 20 or at a cost of 20. And my predecessor there is E. Right? Okay. I did that. Oops. I did that by taking out this vertex right here. Let me go ahead and start another final distances over here. And I'm actually going to put that as a triple. There we go. Now, the interpretation here is, again, this is the vertex, the distance to that vertex, and the predecessor to get there. So initially I'm going to pull out the minimum one, okay? There was only one option there before the 0 one. Everything else had an infinite distance away. It was an infinite distance away. I can't get there yet. I haven't seen how to get there yet. And so I've got E. I can get there at a distance of 0 because I start there. And of course, there's no point in identifying the predecessor vertex here because you're at E. You're not going anywhere, right? Next iteration. What I do is I look through the list over here and I pull out the minimum one. I've got a minimum distance one, okay? Now, there's several infinites. There's 2 5s and 120. Obviously, I take the minimum because I'm trying to find the minimum distance from a vertex to any other vertex. I've got a tie here, though, B and D. So break ties arbitrarily. It doesn't really matter. I'll go ahead and break ties lexicographically and pull that out and put it over here in the final distances, right? Once that's in the final distances, I am done, right? I never visit that. I never consider that that triple again, okay? But what I now need to do is what I need to say is I can now get to B. And let me make it a little bit thicker. There we go. I can now get to B using this vertex right here at a weight of 5. I've fixed that. I've pulled that out of consideration and put it over here in the final distances. I now need to say, well, what else can I get to now that I've finalized B? From B, if I look at its neighborhood here, at the outgoing neighborhood only, I can now see A. Right? I can now get to A at a distance of 7? No, not a distance of 7, but it cost me $5, cents, whatever, distance 5 to get to B. So what I need to do is, I can get to B at a distance of 5. I can now see A. I can get there at a distance of 7. So total 12. Is that better than what I've found so far? Well, anything's better than infinite. So I'll go ahead and update that. I will also keep track of how did I get there? I got there through B. Right? Now, there's nothing else here to update because I can't go from B to D directly or B back to E. I wouldn't want to do that anyway. And that's the only thing that gets updated here. Okay? Next iteration, I pull out the minimum one, which is still going to be this one that's weighted 5 over here. And so I'll put that over here. And I'm fixing that one. So D, I can go to D from E at a distance, total distance of 5. And I'll go ahead and pull it out of here. and that's gone. All right? That's fixing this edge right here. Okay? But now I look at D's neighborhood, which is quite large, and there's a whole bunch of things that I can now get to. From D, I can go to B at a distance of 5 plus 15. Well, I've already taken care of it over here. It's already out, so I don't need to do that. Right? I only need to consider things in the neighborhood that are still under consideration over here, not things that I've finalized the distance on. But now D can go to A at a distance of 5. Is that better or not? Well, how did I get there? Well, I got there from D at a distance of 5, right, from E. And to go from D over to A would only cost me 5 more. So the total distance there is 10. Is that better than what I've found so far? 12. Yes. So I forget that alternate path from going from E to B to A, and I say, well, now I can go to D. So I will update this as the minimum distance 10, and my predecessor is no longer B. How did you get there? I got there through D. Right? Likewise, other things are updated here. I can go to C at a distance of 5 plus 20, so 25 is better than infinite, and I got there through D. F, I can get there at a distance of 5 plus 20, so again, 25, and I got there through D. Now I can see G at a distance of 5 plus 10, 15. Is that better or worse than what we've found so far? It's better. 15 is less than 20, so I will update that as well. Okay? Good. What do we do next? We pull out the minimum one. This triple is the minimum, so I'll take that out. There we go. And that is, again, kind of like fixing this edge over here. I went from A to D, or from D to A, excuse me. Right? So I fixed that, and I've pulled that out of consideration. And no other path to A will end up getting me here. Okay. All right. So, what's next? Oh, no, what's next is I need to update A now. But A is a sink, so nothing ends up getting updated because its neighborhood is empty here. Okay. Next iteration, I pull out the minimum, which is going to be G. There we go. From D. There's my triple. And I've fixed this edge right here. And now I need to update anything that is in G's neighborhood here. Well, there are only two outgoing vertices here, going to F and I. So let's consider F. How did I get to G? Well, I got there through D at a total cost of 15. That's why I'm only keeping track of this one number here, not the entire path. Implicitly, through the predecessor vertices, I am keeping track of the entire path. But I'm only keeping track of one number here. I'm not keeping track of the entire path information because I can actually rebuild that later. And I'll show you how. So I can go to F and I can go to I. Right? F, originally it was 25, but now it's 15 plus 10. Well, that's 25. There's no reason to prefer one or the other over the other, so I'm not going to bother updating that. But now I can get to I at a total cost of 15 plus however much it costs me to get to from G to I, 5. So that's going to be 20. And the predecessor there is G. Okay. Good. Next iteration, I will pull out G. Right? And from D. Oops. Oops, I already did that. Sorry. Yeah, I already pulled that out over there. Right? From D. And so the next one is actually I. So let me go ahead and draw that. I will pull this one out at a total cost of 20 to get to I. And I'll just go ahead and type it out over here. I, 20, and G. Right? And then I can get rid of it over here. Okay. But I do need to look at its neighborhood. Its outgoing neighborhood, one of them goes back to G. Well, there's no reason that I would ever do that from E here. So I'm not going to reconsider that. But now I can get to F at a cost of 5 from I. From I can get at a cost of 20. So total 25. Is that better or worse than what I've found so far? It's no better. So we won't end up updating that. Okay. All right. I think I forgot one. J, H, I, J. Yeah. J should have been in there the entire time. And sorry. There. It's not going to matter because hopefully you can see immediately that H and J are going to end up not being reachable from E at all because H is a universal source and J, the only incoming edge is from H. So there's no way to get to either one of them from E. Right? Next iteration, I'll go ahead and pull out C. Go lexicographic there. C, 25, and D. And that is going from this edge right here. And then it's not that interesting anymore because, of course, the neighborhood here, C to A, there's no change there. So I'll go ahead and pull this out. Update the neighborhood, update any vertices here, etc. And I'm good to go. Right? All right. Next iteration, I would pull out F. And from F, nothing's going to change at this point. F, 25, and D, and H, inf, no predecessor, and J, inf, no predecessor. That information is still retained, by the way. All right. 1 second. There is something I need to take care of, so I will be back in 30 seconds here. All right, thank you. Sorry for that. I just had to close the window. I don't know if it was picking it up or not, but there was a mower in the background. All right, so there is Dijkstra's algorithm run on... Oh, and then I forgot to draw the last edge there. Sorry. When I pulled out F, that it should be like this. There we go. And those are that's the final... that's the final state of Dijkstra's algorithm. Right? Now, we were keeping track of these predecessor vertices throughout the entire process so that we could rebuild these pathways right here. And the way that you do that is simply saying, well, from E, remember, it's a single source, shortest distance. So if you want to go from E to any other vertex, there could be a different path and a shorter path going from, say, G to I, right? At or some two other arbitrary vertices. There could be an even shorter path than what was built by this tree, basically a tree. But that's not what the point of Dijkstra's algorithm. Dijkstra's is a single source shortest path algorithm. Whatever you start at, that'll produce the shortest path to every other vertex. And of course, for some of them, it'll be an infinite path because infinitely weighted path because you can't get there. Okay. How do you reconstruct these paths? You just simply ask, Well, how did I get to I? Well, we know from the picture here, you go from E to D to G over to I. But with just this information, this data down here, how do you reconstruct that path? So let me go ahead and move it over here. Oops. Oop, didn't want a duplicate. There we go. All right. How do we reconstruct this path? Let's say I, right? Well, I started, I say, well, how do I get to I? In fact, I'm going to go ahead and do it over here on this piece of paper. How do I get to I? I need to know how I got there. And so I'm going to go ahead and look at, can I move it? It moves when you don't want it to, and then doesn't move when you do want it to. All right. So not even looking at the picture here. In fact, I'll cover up the picture entirely. All right. Don't look at the picture. All right? How do I get to I? I look up its triple, and I got there through a predecessor of G. So the answer is, well, first you have to get to G. Well, now how do I get to G? I look at its triple. I got there through D. Okay, that's great. How did I get there? Again, I want to go from E over to I. How do I get there? Well, I have to do this until I get over to E. How did I get from D? Well, you went there from E. And then there's your answer. This is how you can reconstruct the path just using those predecessor vertices. And it also tells you what the distance is. Well, that's a distance of 20. And so you can reconstruct the path. You have all these triples are sufficient to not only tell you what the shortest path is, but also what's the total weight of the shortest path. Okay. And that's a pretty easy algorithm to come up with. I'm not going to do it, but I will do it for the version of Floyd-Warshall's that we're going to look at here in a second. First of all, any questions? I don't see any. So we'll go ahead and continue here with Floyd-Warshall's. So again, Dijkstra's only produces a single source shortest path algorithm. It updates a list of triples, which include a vertex, distance to the vertex from S, and the predecessor, or how to get there. All right. What kind of data structure should we use for all this stuff? Probably, again, a min heap or priority queue to store references to the vertices. Right. But one of the big differences here when we actually write the pseudocode is that you're also going to need the ability to update priorities, update the weights. When using the min heap, you need the ability to update the priority or weight. Right? Just like we did over here, we found a better path, and so we updated the weight in there, which means that on the next iteration, that one could have jumped to the front of the line as far as our priority goes. And we saw that a couple of times. So you are going to have to keep track of that and use a data structure that supports that. Right? And we'll see that in here in a second. And I'll talk a little bit about how to do that in practice. But let's go ahead and take a look at the full pseudocode. Okay, yeah, I do have full pseudocode here. Right. So again, this is Dijkstra's. And the input, again, it is a single source shortest path. So the input could be a directed or undirected graph. G, V, comma, E, with edge weights. Right. And a source vertex, S, in the vertex set. So as part of the input, you do need to specify which vertex are you talking about? Which edge vertex do you want to start at? Because it only finds the minimum path to all the other vertices. So if you want to find the minimum path from any two arbitrary vertices, you would need to potentially run Dijkstra's over and over again for each vertex. Okay. Our output will be a table of triples as described before. Vertex, min distance, and predecessor. That then you'll be able to find the reconstruct the minimum distance path, and also be able to tell how what its distance is. So again, this time I will go ahead and use Q. Right, this is a min heap priority queue, and it has to be updatable. Right. In other words, you're putting something into the queue. Not only that, but you need to say that, okay, well, its distance, its weight has changed, which may mean that it goes up in the queue or it goes down in the queue as far as the priority goes. Right? You'll only ever actually be reducing the weight, because if you find another path that is, if the shortest path is so far is 25, and you find another path that's weight 100, well, who cares? You're not going to take that path. So you'll only ever be reducing it. And you can see how you might be able to do this by, well, if it's in the heap already, and it suddenly it has a reduced edge or a reduced priority, all you have to do is heapify it upwards, potentially all the way up to the root, but you only have to look in one direction. You don't have to worry about the fullness property of the heap. So it's actually pretty easy to do. The caveat is that you actually have to find the node that corresponds to that. So the idea is that to be updatable, you'd actually internally have to keep track of two things. You'd have to keep track of the tree, but you'd also have to keep track of a reference to the node that you can jump to, say, using a hash table or something like that. It's not that difficult, but it is a small little detail that you have to take care of in order to make sure that it's going to be continue to be efficient. Right? Otherwise, if you have to search through the entire heap, linear search to find the thing that you're looking for in order to just change its priority and heapify it up, then that's going to be linear search. Arbitrary find methods in a heap are going to be order n. Okay, unless you keep track of other things in another way. Right? So for each, here's our initialization. For each vertex in the vertex set other than S, so I'm taking out S here, this is set minus, vertex set, this is another set, I'm just taking this set out. I'm going to initialize all these triples, right? So D sub V is going to be infinite, right? P sub V, now I was just writing it with a hyphen in the example, but I'll go ahead and use phi here to indicate that it is null or an unknown or something like that. And then I'm going to go ahead and put it in there. Q.NQ V and D sub V. There we go. That's the initialization. Okay. I'm also going to need to initialize everything with respect to S. D sub S, oops, the distance to get to S is going to be 0, of course. The predecessor vertex of S will end up being null, right, or phi in this case. And then I need to put that in there as well. S and D sub S. Okay. And then I'm going I'm going to have to build a vertex set here to be. Do I need to do that? No. I think for the details of the pseudocode, I'll go ahead and maintain it just because. But this is. You are basically building a tree, and so that's why I've labeled this V sub t. This is a vertex set of a tree, and we start out initially nothing, and then as we pull something out of the queue, then we're going to add that to our tree. And we did produce something that looks like a tree over here. It's actually a forest, because H and J are both isolated vertices in the forest because they're not reachable. Okay, but that's the end of my initialization. Now let's get to the actual algorithm. Okay, for I running from 1 up to n. Right, we only have to do this n iterations, just like, say, Huffman coding, where you were building a tree and you knew that if you started out with 10 trees, to combine them all into one tree, you only had to run it 9 times. Well, this, I know that if I put n things into the heap, into the queue, then I know that I just need to take 10 things out. So it's going to be a fixed for loop here, right? And I will dequeue the next item, and that's what I'm fixing here. All right, so I'm going to add that to my tree set. That's the union. Right. And then for each element in the vertex in U's neighborhood here, so I'll go ahead and go with X here. In the neighborhood of U, I'm gonna have to have another paper here. Second. For each vertex in the neighborhood of U, now I need to update. So if the distance to get to U plus the weight of going from U to V, or U to X here, is less than the distance that I've found so far, then I've found a better path. And so what I need to do is I need to update d sub v to be d sub u, because what I've done is I've pulled out u already, right? And from u I can get to x at this distance. I can go from u to x at this weight. How did I? Well, I also need to account for the distance or the weight to get to u, because if I'm going from s to u and then jumping over to x, I need to add those two things together. And if that's less than what I've found so far, then it's certainly better. Plus the weight of u and x. Right? So I update that. I update the predecessor vertex to be, well, how did I get to x? I got there from u. Sorry, this should be x. Yeah, there we go. Don't change variable names on the fly. That's good advice. Q dot decrease priority of v and d sub v. Right? Sorry, dx and d sub x. There we go. And that's the end of all of those for loops. Right? Now, again, this is the key right here. How can you decrease a priority? Well, if you've just got a straight up naive implementation of a priority queue, you can't, because you actually have to find the node or find the index that corresponds to this element right here, depending on how you are implementing it. And an arbitrary find method for a min heap or a queue, a priority queue, is going to end up being order n. And then the heapification process, that's going to be order log n, because heaps guarantee a logarithmic depth, and you only have to do it with respect to its ancestors in the tree, so you can move them up, because you're only ever decreasing the priority. But the key here is that you can jump to that location as long as you're keeping track of two things, right? If you've given x, if you use nodes to represent your heap nodes, then you would keep a hash table that given x would give you the object representation of that node. And then now you're in the middle of the tree. You just basically jumped into the middle of the tree, and you can look at its parents. You've got the node object. Now you can do whatever it needs to be done to decrease the priority. If you are using an array, then what you can do is you can then instead say that x maps to an index in that array, and you maintain, again, a hash set, a hash map in order to maintain that. And of course, you'd also have to update it. That if you do heapify this and decrease the priority and it moves up in the heap, then that means that its index is being changed. And so whatever it changes to, then you would need to update that map as well. Just a small little detail if you're going to do it this way. Okay. But of course, if you're using a standard collections priority queue that supports this anyway, then you're good to go. But otherwise, we'll output all those triples, d sub 1, d sub v1 through d sub vn for all the distances of all the vertices, and the predecessors of all the vertices. Right. From that, you can write another algorithm to rebuild those the actual paths to get there. Okay. Which I believe you have to do for your programming assignment. All right. I'll go ahead and leave the analysis to you. Again, it's probably going to be, as long as you have free access, amortized free access using a hash table or a hash map or something like that, where you can jump to a location in order to decrease the priority. You saw that for loop only ran for n times. You potentially have to update everybody's priority, but it's diminishing. So an amortized analysis would probably lead to something like n squared log n at most. You could probably get that down to n log n by being very careful about your analysis, though. Okay. All right. Still no questions. Remember, we are on Piazza for live questions or comments if you have them. All right, then our last algorithm, and we may not get done with it today, so I'll go ahead and in fact, have plenty of time. Your programming assignment is due on Wednesday, so it's if we only cover the idea today, and then we're going to have plenty of time. We can go ahead and finish this out today. What am I thinking? The pseudocode for this is super simple. All right, so here's another shortest distance algorithm. It's the Floyd-Warshall algorithm. Right. Now, you might have seen this before with, say, maybe in 235 in discrete mathematics, where you talk about transitive closures and computing a transitive closure. It's actually the exact same algorithm, but it's a little bit different criteria. Let me go ahead and visualize it for you. So what we want to do is we want to know what is the shortest distance from v sub I to v sub j. Right? So suppose that we've found a shortest distance so far, and this is d sub ij. Right? And the squiggly line here is some path. There might be many vertices along this path. It might be a single edge along this path. Now, can we get there through an intermediate vertex, v sub k? Right? In other words, I'm going to ask the question, what if I found a path from vi to vk at a distance of dik? And then from vk, I can go over here to vj at a distance of dkj. Right? If this distance is less than this distance, then taking the path that leads me to v sub k first and then over to v sub j is the better path. That's the shorter path. So if d sub ik plus d sub kj is less than d sub ij, then I update my path. Instead of going whatever this path is, I would take this path over here, and then I would take this path over here. Now, the idea here is to ask this question for every pair of vertices. So for each for each vertex v sub I, for each vertex v sub j, ask yourself, can I get to what about this intermediate vertex over here? What if it was this one? What if it was that one? What if it was that one? What if it was that one? Right? There are only n possibilities here. Right? So it immediately suggests a way of doing this, that check for each intermediate vertex. And if that vertex leads to a better path, then go ahead and update it. And in this case, we won't be keeping track of predecessor vertices. We'll be keeping track of successor vertices. Because if I can, what I'm going to do is I want to get from A to B. All right, well, from A, how do you get you first take X, right? Well, how do I get from X to B? Well, next you take Y. And how do I get from X to Y? Well, you just go there directly, right? We're going to keep track of successors, things that come after. With Dijkstra's algorithm, we're keeping track of predecessors. How did we get there, right? Instead, we're going to keep track of where do we go to next in order to get there, right? So we're going to keep track of those two things. One caveat here is that, well, actually, neither one of these algorithms really works on graphs with negatively weighted cycles. So, for example, A, B, C to D, or back to A, at 1, 2, and then negative 10. Right? What's the minimum weight path from A to any other vertex here? Well, it's unbounded negative infinity, basically, because I can exploit this and I can go around this as many times as I want and find an even smaller path, right? That's not a simple path, though. So does this work for simple paths? Dijkstra's would. That'll find the minimum weighted path in a graph, even a simple path in a graph, even if there are negatively weighted cycles. But unfortunately, Floyd-Warshall's does not work like that. Right? So be careful. That is one caveat. All right, so here's we're going to take a little bit different approach to this. What I'm going to do is I'm going to write the pseudocode for this first, and then we'll run through an example. Because the idea that I just illustrated of simply iterating through each vertex and asking, well, what if I go to this vertex first? The path that leads to that vertex, then the path that leads to that from that vertex to the destination that I want to go to, is that better or not? Okay. And so the pseudocode to do this is super, super easy. Right? It's only 3 lines. If you've seen Warshall's algorithm for transitive closure, it's exactly the same thing. So my input here is going to be a weighted graph, G. And it can be directed or undirected. We'll, of course, stick with directed graphs here, but it works on either one. Our output will be a min distance matrix D and a successor matrix S. Okay? Both of these are going to be n by n matrices. Because if we've got a directed weighted graph, then going from the path that goes from A to B might be completely different than the path that goes from B to A. In fact, there might be a path from A to B and no path from B to A because of the directedness. Okay. So D here is going to end up being an n by n matrix. And I need to initialize it. I'll also do S at the same time. S will be an n by n successor matrix. So just set those up as you will. And then for I and j running from 1 up to n. In other words, let me go ahead and write this out for I running from 1 up to n, for j running from 1 up to n. I'm just using this shorthand here, right? And in the notes, I think I actually used even more shorthand. Mathematically, you can say I comma j runs from 1 up to n, right? So for I and j running in each one of these combinations, in other words, you're going to have to do it for every entry in both of these matrices. D sub ij is going to end up being the weight of going from v sub i to v sub j. In other words, the edge weight. We initialize this distance to all the single edges, okay? And infinity if no edge. In other words, this is nothing more than an adjacency matrix. We initialize it to the adjacency matrix of G up here. And then our successor is simply going to be J for all edges v sub I, v sub j. Right? And then nil phi otherwise. Right. So if there's no edge, you can't get if there's no edge from I to j, you can't get to j from I. But if there is an edge from I to j, well, how did you get there? How do you go from I to j? Well, you just go to j. And that's what this initialization here is. Otherwise, phi indicates how do you get from I to j? Well, there's no edge from I to j. There might be a path there, but we haven't found it yet. So I'll just go ahead and set it to null or nil. Right? Okay. That's the initialization right there. Now, for the really super simple algorithm. All we need to do is run 3 for loops. For k, running from 1 up to n, this is for each intermediate vertex. Right? So I'm asking the question of, well, what if I instead of going from A to B, what if I went from A to V sub 1 first, and then over to B? What if I went from, and then the next question would be, what if I went from A to V2, then on to B? Or the third iteration would be asking the question for V3, V4, etc., etc. Right? You need to ask this question for every single pair. So for I running from 1 up to n, for j running from 1 up to n, right? Then you make that condition. If, move this up. If d sub I j is greater than d sub I k plus d sub k j. Right? I already wrote that, so otherwise I wish I would have taken that back and rewrote it the other way like I did over there. Then we've found a shorter path by going to k. Right? Going from I to k and then from k to j, the sum of that distance is going to be less than what I've found so far. So I update d sub I j to be d sub I k plus d sub k j. I also need to update my successor matrix. If I the question here is, what is the successor of going from I to j? In other words, if I want to go from v sub I to v sub j, v sub I to v sub j, where do I go first? Right? Where do I immediately go first? Now, whatever that was before, I don't care. But now it's going to end up being, well, you go to k first. Right? But you have to be careful. How did I get to k? Right? That's stored in the successor matrix already. How do I get to k from I? Right? I want to go to v sub k first. Well, there might be an entire path. That might not be an edge. That might be a path. How do I know, how do I get from I to k? Well, the successor matrix tells me that. I need to go from I to k. Whatever's stored in that successor matrix will update. That's what I want. Right. 3 for loops. The analysis should be pretty straightforward here. This is probably going to be order n cubed. But you have to be careful, again, because what is your input and what is your input size? If your input size is the adjacency matrix already, and you're simply just initializing D to be that adjacency matrix and then updating it, then your input size would end up being n squared. And so this is not exactly cubic anymore. Instead, it would be end up being order n to the 1.5. So not exactly quadratic either, but certainly, unfortunately, not linear, right? Depending on the input size. and how you represent the input. At the end, you just output D and S. Now, let's look at an example. And I'm going to want them side by side, so... Okay. Let me grab this screenshot then. Okay. Here's a graph. Nice little graph. It's going to be pretty bad resolution potato quality there because I just did a quick screen grab over there. All right. So let's go ahead and look at the initialization, and then what I'm going to do is I'm going to fast forward and jump to somewhere inside the some iteration in the algorithm. I need to set up an adjacency matrix here. So here's the adjacency matrix, and I'm just going to simply say A, B, C, D, and E. All right? Okay. Let's try it with this. And A, B, C, D, and E. There we go. So going from A to A, well, that has a cost of 0, right? Now, that's going to be the same along the entire diagonal here, right? This is an adjacency matrix representation. So what distance can I go from A to B here? Well, it's 1 because that edge is right there. Right? I can just jump there right now. A to E, there is no edge, so that would be infinite. A to C, I can get there 2. I should have started in order there. I can go from A to C with a weight of 2. D and E have no edges, so that's going to be initialized to infinity there. From B, I can go to E and D at a weight of 2 and 8 respectively. And then everything else is going to be infinite. I can't get from B to anywhere else with just one edge, with no intermediary. C, I can only get to D at a cost of 5. So infinite, infinite, infinite. From D, I can only get to B at a cost of 4. So infinite, infinite, infinite. E, I can get there at a cost to D at a cost of 3. Everything else is infinite. Right? That's the weighted matrix. What about the successor matrix? The successor matrix looks somewhat like this in that if there's an infinity here, then that's going to be null. I mean, you can't get there, right? So how do you go from A to A? Well, okay, we can go ahead and initialize that to A. B to B, C to C, D to D, E to E. How do I get from A to B? Well, you just go to B. So B. How do you go from A to C? It's just going to be C. And then these are going to be nil or null or missing or whatever you want to call it. Anywhere I have an infinite over here, it's going to be, you can't get there. So no, it doesn't work. How do you get from D to B? Well, it's just going to be B. Infinity, infinity, infinity. And I think I'm losing the forest for the trees here. Infinity. We should have gone row by row. How do I go from B to D? Well, you just go to D. How do I go from B to E? You just go to E. How do I go from C to D? You just go to D. And then I can't, and I can't. There we go. That's the successor matrix, the initialization. What I'm going to do is I'm going to jump into the middle of the algorithm here. ... The first iteration would ask, well, what can I get to? Actually, I'm just going to jump to the second iteration. The first iteration of Floyd-Warshall's algorithm would have K being 1. So you're asking the question for each pair of vertices, C, D, D, C, E, B, etc., etc. What if I went to A first? Well, you can see that A is a universal source. So all those questions are going to be, you can't do any better. You can't do any better because you can't get to A. Right? It's only in the second iteration where I ask the question for, what if V sub K is B? In other words, what if I use B as my intermediate vertex here? And we're only going to look at a part of it. But fast forward here, 0, 1, A to B, yeah. All right, and now I'm going to ask the question, what about going from A to C? Before that had a cost of 2. But what if I went to B first? What if I went from A to B and then over to C? Right? Well, B to C, that's infinite, so that's not going to update, is it? Nope. So infinity versus 2, you're still going to have 2. A, B, C, D, E. But now here's where things start to get interesting and actually start changing. The question for this one is going to be, if I go from A to, I want to go from A to D, right? What if I went from A to B and then from B to D, right? Well, A to D, I can't get there directly, and so that's currently infinity. But I can go from A to B at a cost of 1. I can go from B to D at a cost of 8. Should update it, yep. So 9 is certainly less than infinity. And so I would update this 9 here. Down here, I would update this nil. How do I get there? How do I get from A to D? Well, you first go to B. So I would update the predecessor there to B. Similarly, what if I went from, my question is, how do I go from A to E? Oops, A to E. Right. Well, currently you can't, or it would cost you infinitely many dollars or whatever you're trying to capture here. But what if I went from A to B? Again, my intermediate here is B. What if I went from A to B and then over to D? Well, I consult my distance matrix here. I can go from A to B at a cost of 1. And I can go from B to D at a cost of 8. It's not. Oh, sorry. This should be E. There. B to E at a cost of 2. So 3 is certainly better than infinity. And I also update my predecessor. How do I go from A to E? Well, first you go to B. Right. Each one of these things would get updated on each iteration potentially. If they don't get updated, that just means that you have not found a path, or you found another path that is even worse than the original path. Right? What I'm going to do is I'm going to super fast forward here to the end, new paper, and show you what the same graph here, show you what the distance matrix looks like and the successor matrix looks like. So the distance matrix is going to be 0, 1, 2, 6, and 3. Note here that got updated even more. We found another path eventually that's even smaller. Remember that going from A to D, well, we found 1, 8, and then eventually we're going to find that we can go from A to B to E to D at a cost of 1 plus 2 plus 3, 6. Right? And we only know that by asking the questions about A, B. What if B is what if A is the intermediary? What if B is the intermediary? What if C or D or E are the intermediaries? Right? This will remain infinite. B to A. How do you get from B to A? You can't, because A is a universal source. So this will be 0, infinite. Again, how do you go from B to C? You can't, because you'd have to get to A first, and the A is a universal source. So that'll remain infinite. 5 and 2. In fact, I can go ahead and put all of these infinites here, because from any vertex, how do you get to A? You can't. Right? This is going to be 9, 4, and 7. This will be 0. 0 is on the diagonal, remember? Infinite and infinite. 3, 5, 11, and 6. And this is actually a great test case if you want to use this, not for one of your official test cases, but you can use this to troubleshoot to see if this is the matrix that you get if you're going to choose to use Floyd-Warshall's algorithm. Here's the successor matrix. Nothing. Anywhere that you see a 0, I guess we initialized all those to A, B, C, D, but of course you can always check and well, I'm already there. I don't need to go from A to A. You don't have to keep track of that. B, C, B, B, nothing, nothing, E, E, D, nothing, D, D, B, nothing, nothing, B, D, nothing, D, and nothing. There we go. I could have just taken a snapshot of that too, I guess. But what I wanted to do is I wanted to fast forward to the end of the algorithm to show you how you can use this successor matrix and this distance matrix in order to reproduce the path. Let's go ahead and look at one of the more complicated ones. How do you go from A to, let's say, D? Right. So what you do is you look at the successor matrix, A to D, and you say, oh, the answer is first you go to B. Right? So I've built a path so far. I go from A directly to B, so this is why it's not a squiggly line. And then now I've changed the question. Now, well, how do I get to D still? So ask the same question. How do you get from B to D? You look at the successor matrix. B to D. Okay, first you go to E. Again, the question would be, how do you go from B to D? First, you go to, again, B to D, E. So that gives me another piece of the path. First you go to E. Well, now the question becomes, how do I go from E to D? And I won't rewrite the question this time. E to D, it simply says, well, just go there. And so this gives me a path of A to B to E to D as my shortest path from going from A to D. Let's visualize it up here. A to B to E to D, like I said before. And it's going to be 1 plus 2 plus 3 at a total distance of 6. And that's what's being stored up here. Okay? So much simpler pseudocode, a little bit more sophisticated. It's essentially the same code here, pseudocode to reproduce this actual path. As a last thing today, let's go ahead and write that pseudocode. And as you might imagine, all you have to do is a simple while loop. Right? Let's go ahead and be rigorous about it, though. Right? My input is going to be a successor matrix S from Floyd-Warshall's algorithm, and 2 vertices, v sub I and v sub j. Right? And our output will be the min distance path. It's just going to be a list of vertices, vi to vj. Right? I like that squiggly arrow there that denotes a path, right? And a straight arrow would denote a direct single edge kind of path. Right? So we will start our path at vi, because again it is directed, so you have a source and a destination. So you start at your source. And I will need to keep track of the current vertex that I'm at, because then I'm going to ask the question, well, how do I go from x to v sub j? Right? Then I need to update my x. So I'll start it at v sub I. While x is not equal to v sub j, while the current vertex has not reached its destination yet, then I will update x to be whatever is in the successor matrix of going from x to v sub j. Again, I'm asking the question, I'm at x, how do I go from x to v sub j? Right? And that's stored in this successor matrix right here. I will then add that to the path. And again, we used this syntax before, this pseudocode syntax of I'm just appending X to the end of this path. That's it. Output the path. Right. You're just following in the matrix. Okay, well, how do I get from A to B? First, you go to here. All right, how do I go from here to B? Well, first you go here. How do I get from here to B? Well, to my destination. Well, next you go there. Eventually, it's going to say, well, just go there, because there's a direct edge connection between the two. Right? And that's it. Clearly, this is going to be order n, because you could get into a situation where the minimum distance path ends up visiting every single vertex. And you can have an example like that. In fact, in the book or in the lecture notes, I give an example. This is the worst case scenario where every iteration of Floyd-Warshall's is going to end up updating all the most of the matrix entries. And the minimum distance path from A to E here is going to end up visiting everything, because this is called a tournament. It's called a tournament because you have everybody plays everybody else, right? A plays B, and B also plays A. A plays C. And it's kind of an ordered tournament where it turned out nice, and you didn't have some cycle that Team A beat Team B, Team B beat Team C, but C beat A, right? You don't have that kind of cycle in this tournament here. But I've intentionally made them a weight such that going from A to E, well, initially that's only one edge right here at a cost of 15. But on the next iteration, we ask, well, wait, what if we went from A to E through B? Then that would mean that we would see this edge here at 1, and then jumping over to E at a weight of 10, 11 is going to be better than the 15 that we initially started with. Then you ask the question again, well, what if we went to C first, right? If we went from A to B to C and then over to E, and you'd find a path that's even shorter, 1, 2, and then 5, so 7, right? Then you'd ask, well, what if we went to D? 1, 2, 3, and then D jumps over to E at 4 is even better than 7, right? So this is an example that shows you actually have to ask the question about every single vertex. You can't get away with cutting short, and that's why you also have to ask the question even of sources here, and also the resulting shortest path ends up being the longest path with respect to the number of edges. It's just that the edges are all weighted such that that ends up costing you less. Right? So it's kind of a difference between a distance of driving distance going from, say, Lincoln to Chicago, right? There's a direct route there. There's a direct flight there, say, and that's the minimum distance because you just go there straight. But it also costs way more than driving, and driving means that you're going to have a longer distance. You're going to drive a greater distance, but at a lesser cost because you're only paying for gas at that point. Okay. All right. I see no questions. That really concludes our coverage of graph algorithms. And we'll start on our next topic, which is dynamic programming. And that's why I wait for Floyd-Warshall's to the last, because it's actually an instance of dynamic programming. Dynamic programming can be seen as basically a divide and conquer approach where you flip the divide and conquer. So divide and conquer approaches usually are recursive, so you break the problem down into smaller and smaller problems. Well, that's a great first step. But what you can then do with dynamic programming is that you can look at the bottom of that computation, and you can look at the smallest subproblems, and then you can say, I'm just going to go ahead and solve those directly, and then for a bottom-up solution, I will start with the solutions to those smaller problems, and I'll start combining them to create a solution to the larger problem, right? So instead of breaking a problem down, I mean, it's part of this problem-solving process where you break a problem down into smaller and smaller problems. But dynamic programming has you actually solving it by starting at the bottom and then working your way up after you've solved it. It's kind of It goes back to one of my themes for Computer Science 1, that computers don't solve problems, you do, right? Computers only automate solutions. And so that's what kind of dynamic programming is. You still have to come up with a solution yourself. But dynamic programming means that when you automate a solution, you don't implement the recursion. Instead, you build this. We call them tables or tableaus if you want to be fancier. You build a tableau and then use entries in the tableau as a cache to compute other entries in the tableau, working your way up to one cell in the table. And that's your solution for the actual problem. We'll start on that tomorrow. Okay? Have a good day.